Cal to maybe implement some of the things he just talked about. So this is a movie showing the performance for the La Habra event. The red stations turn red when they exceed MMI 4, and it predicts out to 30 kilometers in yellow, and then you can see as more stations turn red, they actually experience MMI 4. So this is Southern California, so the whole thing actually works, which we were really excited about. Here's just a snapshot of that movie at 3 seconds, 8 seconds, 13 seconds, and then it's overlaid on an MMI shape map. So you can see that MMI 4 regions generally encompassed by these red circles, and it doesn't overpredict out to farther distances. So that's just how PLUM works. Again, so this is what we're running in Southern California. And it's the undamped version. So if the ground motion exceeds some threshold, then it sends the alert to that same radius, and if it's not exceeded, then nothing happens. So we wanted to explore what thresholds are best to maximize our event detection in Southern California. So this is an example of, for a single station method, it ingests current MMI feeds from the shake alert system, calculate MMI using the quadrature sum of 3 components. If it's above the station, you declare an event. If the first station falls below the threshold, you cancel the event. And if we look at a 2-station method, then a neighboring station has to exceed a secondary threshold within 15 seconds of that first station. And we create a station mesh, they have to be neighboring stations. And we explored different primary thresholds of MMI and then different delta MMIs to create a secondary threshold. So that's down here. So instance 1 is using a single station. Instance 2 means that both stations have to have the same MMI. Down to instance 6, which is actually our preferred, it means that change in MMI is 1.5 MMI. So the first station triggers, for example, MMI 4, the second at 2.5. And then to put it into sort of shake alert event detection space, we associated the stations that turn on with events in the catalog that had to fit sort of into this wedge of P-wave and S-wave travel times to become associated with the event based on catalog locations. And again, we're not evaluating ground motion accuracy. So this is an example from SoCal. This is our station mesh. You can see how the stations are associated and the test events that we ran. This is from 5 years or 6 years, I think, of Southern California data magnitudes 3.5 and larger, 193 events. We pulled 7-minute waveforms, all consistent with shake alert testing and certification. And we also tested historic and problematic data set. Again, this is consistent with shake alert testing and certification. These are large or interesting events, teleseismic calibration, noise spikes, and these have caused some of the shake alert algorithms to issue false alerts or have a little bit of difficulty. So this is the SoCal magnitude 3.5 data set. Again, the goals here were to identify all magnitude 5 events and minimize the false alerts. So you can see this is a single station instance, and then these are instances where both stations are first and second station have MMI 4, and then this is the first station, the second station is MMI 2.5. So you can see the number of events colored by magnitude, and we're able to identify all the magnitude 5s and across almost all instances the magnitude 4.5s to 5s. If we decrease the secondary MMI threshold, so that's this one, we detect more small events and continue to detect the larger events. So we're just going to sort of compare the single station and the 2-station. We see here that with 2 stations, we can reduce the number of false alerts. So in the end, this is our preferred setup here at initial threshold MMI 4. So this is just more of the same, but it says this is the Southern California and the testing and certification. For primary threshold 4 and secondary threshold 2.5, we get no false alerts and no missed magnitude 5 events. Same down here, except we are unable to detect a magnitude 5 event that's coming from Baja, California, but no false alerts here. So, and then this is the alert latency. Again, this is the preferred in the middle, so it's about 5 seconds on average, but there's obviously quite a spread. So again, our preferred setup is this 2-station, MMI4, MMI 2.5. And these latencies, I should mention, don't include data transmission or communication, so just what the system is seeing. All right, so then we move on with that same thresholds of MMI4, MMI 2.5 onto the entire West Coast. This spans the range of the Shake Alert system. So over that same time period for the same magnitude 3.5 and larger, there's 558 events and 20 larger events. So PLUM was able to detect 5 out of 20 of the events. The detected events are in green, so you can see all of the on-land events with the exception of these sparse ones here, and even one of the offshore is able to be identified. The rest of the offshore events are not able to be identified. They don't generate MMI or ground motion on land. There's no false alerts, and there are 2 missed events here where there's the station's not spacing is not dense. We're also running in real time. So this is running from the Shake Alert feeds. It's been running since January, and this is as of a week or so ago. There was 128 event detections, and 107 of those, that's this outer band, were actual earthquakes. And then the 17, there were no false alerts. 17% are missed, or sorry, 17% are actually false. But we're not calling them false alerts here because we understand where they're coming from. Typically, single stations or sets of stations that are really noisy. So here's an example. This is actually from a police gun range target practice in Southern California. You can see these shots, bang, 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 going off, and PLUM detected that as an event right here, and this is spectrogram. So this is something that we're thinking about how to deal with if it's particular stations. We know that this station in SoCal is continually seeing this target practice, so how to deal with that. And then, oh yeah, that's just, I'll get to the ridge crest in a second. Yeah, and there's other examples of stations where we're consistently seeing noisy events that are causing PLUM to trigger. This is the real-time performance from the 2 ridge crest events, the magnitude 6.4, I guess foreshock, and the 7.1 aftershock. Just saying PLUM detected both of these events, took about 5 seconds to pick up the 6.4 and 6 seconds to pick up the 7.1, compared pretty well, slightly faster than the Epic and Finder. And this is just showing the MMIs coming in across the stations, with the color being the MMI, sort of wave train moving out there. All right, so to summarize, preferred configuration from exhaustive tests in SoCal to detect events magnitude 5 and greater is a 2-station trigger, MMI 4, MMI 2.5. For that same Southern California test set, there's no missed events for these magnitude 5s and no false alerts. Does similarly well for the historic and problematic events. West Coast wide, we miss events that are in, offshore in the regions of sparse station coverage, but no false alerts. In the real-time PLUM, we're detecting 83% real earthquakes, and the other ones are false alerts that are station issues or some actual noise, but non-earthquake related. And the median PLUM alert times on average seem to be slightly faster than the Shake Alert algorithm, current Shake Alert algorithms. I think it was that. So some things we want to investigate in the future are how should we be doing the alerting regions? The grids are polygons. PLUM was developed in Japan where there's the idea of sub-prefecture, so it's very obvious how to alert there perhaps. We don't have that in the US, so how should we be best alerting to maximize alerts? And we need to do ground motion study of how accurate are these alerts going out in ground motion space. So modify some of these configurations, and as Yuki just mentioned, add damping and attenuation. We also don't have any site amplification terms in this version of PLUM, so that's something we want to explore as well. And then ideally, ultimately, get it going in real time on the Shake Alert systems. That's it. Thank you.
Thank you. Any comment or question?
So as you know, Shakealert's also running a finder algorithm, which is essentially also looking at sort of ground shaking. So where do you see the advantages and disadvantages of PLUM relative to Finder as the two algorithms under consideration for Shakealert?
Yeah, so I think it's, I'm not sure exactly why, but PLUM seems to be working a little bit faster than Finder, but right now it doesn't have any attenuation, so Finder does. So PLUM would be over predicting in ground motion space in general. And again, because I think Finder's looking for some finite fault, it doesn't seem to turn on until you get to the larger events. And PLUM is able to detect a lot of the smaller events, whether we want to be alerting on those or not, but if they're generating MMI4, interesting. But I think Finder will probably be more accurate to the larger events. Yeah, something Doug and I were just talking about is how can we start combining all these ideas to get the best alerts. I'm not sure.
Okay, thank you. Next is the Becky role. And the title is matching waveform envelopes for earthquake source parameter determination.
Alright, hello, my name is Becky Rowe, and I'm a graduate student in Tom Heaton's group at Caltech. And today I'll be going over the algorithm that we've been working on that matches waveform envelopes for earthquake source parameter determination. So before I go into the details of the algorithm, I'd like to go over the inspiration and goals behind it. As most of you know, the main goal of earthquake early warning is to determine the location, origin time, and the magnitude of the earthquake using the first few seconds of the P wave. And then from there, we want to determine the spatial distribution of the anticipated peak ground motions using attenuation relationships. Now, the particular challenges that we want to address using our algorithm is to improve the robustness of the parameter estimates for the incoming observed earthquake. We also want to find estimates for complex sequences, as current existing algorithms may have difficulty in doing so. But for today's talk, I'll be going over the first challenge, which is to improve the parameter estimates. So we introduced to you a two-part algorithm. And both parts use envelopes and not the full waveforms. The use of these envelopes allows us to examine the shape and the relative frequency to estimate the magnitude and the location. We use the acceleration envelopes to characterize the high frequency content and the velocity envelopes to characterize the medium frequency. So the first part of the algorithm is a standard grid search, and it uses the Kua-Heaton ground motion envelopes. And this will give us more of an average estimate of the parameters. The second part of the algorithm is a catalog search, and this part is more specific to the station and channel that we observe. We first look through the most recent earthquakes, such as the ones that are part of a sequence, and then we search further back in earthquake history using a K-dimensional or KD tree search. So I'll first go over the first part of the algorithm, the standard grid search. But before I do, I'd like to go over the background of the Kua-Heaton ground motion envelopes. They are parameterized by a total of only 11 parameters. The envelopes for the P wave, S wave, and the ambient noise are created first. Then we take the square root of the sum of the envelopes, or squared envelopes, to get the final ones that we use for the grid search. The amplitudes are dependent on the magnitude, epicentral distance, and the site conditions, which is rock versus soil. And for the evolution with respect to time, we use a lookup table of travel times. So I'd like to point out that the Kua-Heaton ground motion envelopes do consider this magnitude saturation with respect to distance. It is more pronounced in the acceleration at close distances to large events. They also take into consideration the different site conditions. So the soil sites exhibit a stronger degree of saturation than the rock sites do. So we take the dependents and organize them into 4 grids. We have magnitude, latitude, longitude, and the shifts with respect to time. So just to save computational time, we don't want to look through a large set of grid points. So we set, for the spatial grid, we set a square of size 2 degrees by 2 degrees at increments of 0.1. And we place the first trigger station's location at the center. And that's because we assume that we have a well-distributed station density, distributed enough so that the first or the observed epicenter is nearby the first triggered station. And we have the last grid, which is shifting the envelopes forward and backwards in time to account for any late arrivals of the signal. So given the magnitude and distance at a grid point, the corresponding cohesion envelopes are created. So once we have the envelopes, we can finally assess the goodness of fit. And in other words, we evaluate how well the cohesion envelopes fits the incoming observed ground motion envelope. And we define this incoming envelope as a collection of maximum absolute values over 1 second windows. So we compute and maximize the probability to quantitatively assess the goodness of fit. And we update the probabilities once more data is available. And this is very simple because the grids remain the same throughout, and all we need to do is multiply the new probabilities to the previous ones. So I will demonstrate the steps that I just mentioned using this real magnitude 4.17 earthquake. This one occurred in Southern California back in 2003. So we collect the data as they come in and compare the envelopes as shown in the left. And we update the probabilities to create this probability plot shown on the right. And so here the triangles represent the stations considered in the grid search. And we see that they are well distributed about the observed epicenter, which is shown in the red X. And the yellow region is the most probable region where the observed earthquake may be located. And in this case, we get the location does converge with an error of around 4 kilometers, and we get a magnitude estimate around 4.19. So we see that it does pretty well in this case using 3 seconds of data from 3 stations. But before I move on, I'd like to point out the grid search is designed to characterize the earthquake as a point source. So if the epicentral distance is less than the finite rupture length, the grid will not be appropriate. But we do have other algorithms like Finder that is better engineered for that type of problem. So moving on with the results, the standard grid search results are robust for magnitudes 4 and 5. The estimates do converge with 3 seconds of data from 3 stations. However, for larger earthquakes, the grid search results may not be as robust as for smaller magnitudes. A better fit may be found using the next part of the algorithm, which is a catalog search, or we can apply a prior directly to the standard grid search. So I'll show that here using this real magnitude 7.1, the main shock in the Ridgecrest earthquake sequence from July of this year. So at 7 seconds after the origin time and from data from 4 stations, we see that the location does converge with an error of 5 kilometers, but it does take more time for the magnitude to converge. And in this case, the grid search overestimated the magnitude to 7.75. However, to minimize the time that it takes to converge and for better accuracy, we can apply a prior. And this prior doesn't require a location estimate. It uses the relative frequencies of the P wave. It takes the ratios of the ground motions at a station, and we use the first trigger station here to find that the magnitude may be 6.97 at 3 seconds after the origin time. So previously I mentioned that the grid search provides more of an average estimate. So how do we provide a check to this? So that's why we have the second part of the algorithm, which is the catalog search. We assume that we have already seen the observed earthquake before in our earthquake history. In this other part of the algorithm, we take in a ground motion envelope observed at a station, and we match it to other envelopes of past earthquakes at that very same station. But searching it by brute force will take time, and we want to minimize that as much as possible. So first we'll search the most recent earthquakes, like the ones in a sequence, and then we can search further back using a larger database by using a k-dimensional or KD tree structure. And these structures are extremely popular nowadays and are used by many services like Google Maps and Facebook's facial recognition to do these fast searches. So here we have the catalog search of the most recent earthquakes first. Let us look back at the Ridgecrest earthquake sequence once more. We know that there were no other previous earthquakes that are bigger than a 7 in the area, but we know that there are many 3s, 4s, and even the 6.4 shock. So we can simulate a larger magnitude earthquake at a given location by convolving the small magnitude observed envelope with a specified time function. This method is known as PLUM spectral scaling model or the omega square model. And so in this case of the 7.1, we can take the previous earthquakes like a 4.97 or a 4.09, or in this case of 6.44 shock, and scale it up to a 7.1 and see how the envelope does in comparison to the grid search. So here in this figure, we have a specific station, Tower 2. And previously you mentioned that the grid search didn't do as well for the magnitude estimate. You can see that here, it's kind of hard to see, but in red, we see the envelope chosen by the grid search, and it doesn't fit as well as it could to the blue observed. So we can scale up the 6.4 that occurred before the main shock and scale it up to a 7.1, which is shown in yellow, and see how it does in comparison. And in this case, the catalog search did fit better than the grid search. What I mean fit better, quantitatively mean a higher probability. So we take this estimate instead of the grid searches for our algorithm. So we can look further back in earthquake history using a larger database. But in this case, we don't want to use brute force search. So we use this method called a k-dimensional or KD tree search. So a KD tree is a reorganized storage of the data points for the purpose of fast retrieval. And the K refers to the amount of dimensions that a data point is characterized by. So a data point may be characterized by like a PGA value, PGV value, different time points, the station that we're looking at. So all that can be considered as a dimension. And the advantage of this KD tree search is that it only looks through a fraction of the entire database. And if the KD tree is built correctly, it will find the global best fits, and not just the local. And as we can see here in the figure, the KD tree becomes more and more valuable as the database grows larger. So that is an important factor to consider. We want the search database to be sufficiently large enough to cover a wide range of potential earthquakes for the KD tree to perform adequately. And so here that we can use the PLUM spectral scaling method that I mentioned previously to expand a small database to a larger one so that we can apply this KD tree search. So in conclusion, our algorithm is simple and direct. The grid search results are robust for the magnitude 4s and 5s, but with larger earthquakes, the magnitude tends to be overestimated. So to address this problem, we apply prior that uses the ratios of the ground motion. And we can also use the second part of the algorithm as a check, which is the catalog search. And so for future work, we hope that the use of these envelopes and the priors will help us detect and identify complex sequences. So earthquakes spaced closely in time. Thank you.
Thank you. Any questions? Okay, so we move on. The next one is a keynote by Toshiba, who will talk about a numerical shape prediction.
thank you very much. So, thank you very much for inviting me to this important conference. And so, thank you very much for the group for inviting me to hear another keynote speech. Okay, so one of the fundamental questions for ASCII early warning is, can ASCII size be determined from the early capture process? Some authors claim, so it is, yes, it is determined. So in this case, moment of magnitude predicted from first to second. On the other hand, many authors say, no, it is not deterministic. So in this case, moment of magnitude not predicted from early capture. So this debate is still ongoing for 20 years. So even JMA method and my talk is based on this approach, so not deterministic. Okay? Not deterministic. So in this case, EW message are updated repeatedly as available data increased with lifestyle. Okay, so one of the important events the last 10 years is of course is earthquake. This animation shows the performance of JMA. So there is a two grade for JMA. One is called forecast, and the other is called warning. So forecast issue in case seismic intensity 4 is predicted, and warning issue seismic intensity 5 or larger is predicted. Here, JMA scale. So even low level alarm, high level alarm. So I plotted waveform observed these four stations, and this is a lifetime from the origin time and first forecast and first warning. So for this aspect, totally 15 messages are issued from JMA, and this shows the number of the EW message and magnitude estimates as a moment. Which shall we go? Okay, ASCII concurrent and P-wave, S-wave radiated from the source. And first station, only detected P-wave, and deep analysis, first forecast and warning issued. So at the time, cell phone, TV broadcast early warning message. Okay, so still weak shaking. First strong ground motion appeared from now on. So first red point appeared from now on. So JMA early about 15 seconds earlier than the strong ground motion. So this is the frequency insurance. Magnitude is estimated to be 7.7. And 12 insurance, magnitude is estimated 7.9. And 13, magnitude is estimated to be 8.0. And 14, magnitude is estimated to be 8.1. And 15, this is the last message. So far, so good. But the problem occurs from now on. So focus on here. Background yellow, which means seismic intensity 4 predicted. But actually, red point appeared like that. So seismic intensity 4 was predicted for Kanto region, but actually seismic intensity 6 observed. So this is under prediction of Kanto region. This is due to the large extent of fault rupture of the magnitude 9 earthquake. But this is the first malfunction. Second malfunction is a false alarm for aftershocks. False alarm means warning was issued, but shake was too weak. This shows the seismic activity, March 5th, March 6th, March. This is a normal station. And March 9, shock. March 11, main shock. So after that, something like that. Aftershock activity quite active. So sometimes multiple aftershock occur simultaneously. In this case, system confused. A system is interprets a multiple event to be a large single event, which leads to overestimation of magnitude and then force. Okay, so addressing these two problems has been our important project last 8 years. And 8 years ago, we started following important question. Hypercentered magnitude, are they the only one approach for EW? And moment magnitude and source event, are they the only method of precise EW? We started these fundamental but important question. And our answer was no. We have a different approach, another tactics, another strategy. And for example, looking at wave propagation from several seconds before, and then predict several seconds later. I will show an example. This is a magnitude 7.4 earthquake. So looking at this animation, let's predict ground shake at Tokyo. Okay. So approaching. Now arrive, now shaking. It's gone. Or something like that. So, okay, so now you successfully predict ground motion at Tokyo. But you didn't care much about hypercenter location, much less magnitude. Anyway, yellow or red approaching to you or not. This is an important information for prediction of ground motion. So based on this idea, we will construct our method. So here, I'd like to clarify. Okay, so prediction arrival. So current observation shading hypercenter magnitude estimated. And using this hypercenter magnitude and also ground motion prediction, prediction shading performance. So two-step approach. So this is something similar in a baseball play. In a baseball, this batter hits the ball, and then this fielder tries to catch it. So in this method, okay, and also even when ball is here, this information is used for the estimation velocity prediction when batter hits the ball. And this guy, using this velocity and prediction, this guy predicts the point ball is falling, and he tries to catch it without watching the ball. Okay. I don't think he's a good player. Okay. Many players play like this. Once obtain this information, this information is not so important. So ball is here, velocity prediction impacts the ball. Okay. So our case, from observation shading directly to prediction shading, so time evolution prediction. Okay, for time evolution prediction, two processes are required. First, how estimate present situation precisely. Second, how predict the future time evolution from the present situation. From viewpoint of solving differential equation, first item corresponds to estimation of initial condition, and the second is a calculation of wave propagation. Okay, so how estimate the present situation, and then how predict the future time evolution. So we experience this kind of prediction every day. So we know very well. So that is weather forecast, especially now numerical weather prediction. In the numerical weather prediction, that is precisely. And using the physical process of atmosphere and physics of thermodynamics, we predict the situation tomorrow and the day after tomorrow. So based on the similar idea, we will perform numerical shape prediction, in which present the situation that is from shaking propagation direction estimated precisely. And then using physics of 10 seconds, 20 seconds, and 30, 40 seconds ahead. So for the first item, most important thing is, of course, observation, enhancement observation. And we will perform correction of site application factor, and we apply data estimation. On calculation of wave propagation, there are several methods. For example, finite differential method or quantum integral application method. These methods are very precise, but it requires much competition time. And we have a radiative transfer theory. This is based on a race theoretical approach. So this is a high frequency approximation, but it requires less computational time. So in this presentation, I explain data estimation, and I use radiative transfer theory for the estimation of wave propagation. Okay, so data estimation. So data estimation is one of the tools to estimate present situation precisely. Okay, so in a data estimation technique, not only current observation, but from the prediction from one time step before, combined, then estimate present situation precisely. So in this case, current observation in this way, one time before observation in this way, two time step before observation in this way. So using all past data present situation is estimated precisely. And so next, focus on this stream. So this means a repeated application of physics of wave propagation, that is simulation of wave propagation. In the simulation, actual data is included. Actual data is assimilated, and simulation of wave propagation is carried out. Okay, so I will have an example. This is a single event case. This is a true wave field and observation by seismometer and estimated wave field using data estimation. This is without data estimation. So compare this one to this one. This comparison indicates a merit to introduce data estimation technique. Okay, shall we go? Okay, so something like that. Okay, so this is a single event case. And next example is a Next is like a multiple event case. Okay, go compare this one and this one. Okay, shall we go? So as you see, more ASCII code, or ASCII code. But it is not easy to estimate for ASCII just looking at this picture, but just looking at this picture. But looking at this picture, okay, and I identify for ASCII. Okay, right? So now it's using data asymmetry technique from all past data present situations is estimated precisely. Okay, so next step is prediction. Prediction for future. For future, we have not obtained observation yet, of course. So simulation of wave propagation, the physics of wave propagation alone repeated that is from this initial condition, simulation of wave propagation is carried out. Okay, so this is estimated wave field using data assumption technique. From this initial condition, we predict situation 10 seconds ahead and 20 seconds ahead. So these are the two wave fields. Okay, for example, this distribution is estimated something like that using data assumption technique. And from this initial condition, using the physics of wave propagation, we predict the situation 10 seconds ahead and 20 seconds ahead. Okay, compare this one to this one, and this one to this one. These comparisons indicate how precise the predictions are. Okay. Looking at these pictures, a friend of mine said to me, no earthquake for this earthquake. Why? Okay. This earthquake has not occurred yet. This earthquake occurred 6 seconds later in future. So it is impossible to predict a ground motion from future earthquake. This is not a problem of earthquake anymore. This is a problem of earthquake prediction. So I will show an example. First example is a single event case. Okay, compare this one and this one, and this one and this one. Okay, shall go. So it looks good. So this is a single event case. So next is a multiple event case. Or compare this one and this one and this one and this one. Okay, shall we go? Okay, so something like that. So data assimilation technique is very powerful. So we apply this method to Tohoku earthquake. And here, I think we did the Tohoku earthquake. This is a sleep distribution of Tohoku earthquake. This is the evolution of seismic moment. And rupture duration is 180 seconds. So probably this is the image of many seismologists. But this is estimated from low frequency. The image of high frequency is very different. Okay? So this is a accelerogram observed G2 stations. So you see more propagation of circular motion, S1, S2, S3, and S4. Okay, so I repeat again, the subject of EW is a prediction of arrival of G's strong ground motion, such as S1 to S4. Okay, so three important things in this figure. So first is okay, so radiation of high frequency is different from that of low frequency. Oh, for example, this is a sleep distribution and strong ground motion generation area S1, S2, and S4, S3 and S4, and the timings of S1, S2, S3, S4. So radiation of high frequency and low frequency different for space and temporary. So second is also this is this phenomenon also observed recent large earthquake, 2004 Sumatra earthquake and 2010 Maui earthquake, and also Tohoku earthquake. Okay, so second is that rupture duration is much larger than the PA portion. For example, around here, PS time is about 30 seconds. But S3, S4 occurred about 106 seconds and 130 seconds. So which means in this information, no information of the radiation of S3 and S4. Okay, so which means the limitation of the on-site method. Okay, so third is okay, so strong strong motion comes from local instantaneous process of fault rupture. So for example, Tohoku region, S1, S2 contribute a lot, but S3, S4 not so much. And Kanto region, S1, S2 contribute not so much, and S3, S4 contribute a lot. So which means strong motion comes from local instantaneous process of fault rupture. So for the prediction of ground motion, all processes are not required. Okay, so this is a result of the numerical shake prediction method. So this is the seismic intensity after correction of site application factor. So we apply data assimilation technique to obtain real-time statement. For this initial condition, we predict the station 10 seconds rate, 20 seconds rate. Okay, shall we go? Propagation of S1. S2. S3, S4 combine them approach to 2. Okay, like this. So the next slide, I will show a snapshot. So 130 seconds, 140 seconds, 150 seconds. For example, at 130 seconds, storm gradient motion observed out here. And we predict this storm gradient motion arrive at Tokyo 20 seconds later. So actually 20 seconds later, that is elapsed time 150 seconds, storm gradient motion actually observed at Tokyo region. Like that. So this is an example of the very large subduction earthquake. So next example is the inland earthquake. So there are 3 magnitude 6.3 events. Tokyo, almost same distance. Shaking at Tokyo, these are almost same, but much different. These 3 earthquakes has already occurred, so we know that result. Okay, so there is a Hakuba earthquake in 2014. B is a Sakai earthquake in 2011, 1 day after Tokyo earthquake. And C is a Chuezu aftershocks. So moment magnitude 6.3 event. Tokyo, almost same distance. Shaking at Tokyo, they are almost same, or very different. Okay, so result is this. Chuezu aftershocks very strong. In terms of PGA, Chuezu aftershock about 9 times stronger than Hakuba earthquake. Maebashi also more than 9 times. Kumagai more than 10 times. Okay. So which means just looking at this picture, just looking at this group, so Chuezu aftershock which made strong land motion despite magnitude 6.3 event. But looking at this group, Hakuba earthquake is the strongest one. And for this group, okay, so in this group, Sakai earthquake is the strongest one. Okay, I will show you examples. Okay, go first. Okay, so this means this picture means precise estimation of habitation magnitude does not necessarily mean precise prediction of the strong motion. Okay, so I will show an example. So this is the first example is a Chuezu aftershock earthquake occurred. And seismic wave propagate. For this earthquake, toward this direction, toward Tokyo, strong shaking propagate. So this phenomenon also without another earthquake occurred around here. So Chuezu main shock itself, and another magnitude 6 class aftershock, and magnitude 5 class earthquake. Toward this direction, toward Tokyo, relatively strong shaking propagate like this. So this is not source factor, this is path factor. Okay, I will show now our prediction. 10 second height and 20 second height prediction. Once we recognize strong shaking toward Tokyo, we predict relatively strong shaking toward Tokyo like this. Okay, so I will show now our prediction from different viewpoints. So seismic wave propagate like this. And this is the eventual distribution of seismic intensity. So actual distribution of seismic intensity is really complicated. For example, it's around here. Okay, so this is a prediction using magnitude 7.0 event and magnitude 6.5 and magnitude 6.0 event. So actual distribution of seismic intensity is really complicated. For example, at the focal area, magnitude 7.0 is a good application, but around here, magnitude 6.0 event is a good example. Okay, I will show our numerical shake prediction. So when we observe up to 11 seconds, okay, up to 11 seconds, the past situation, And this is a present situation. From this initial condition, we predict the future like this. And then we predict eventual distributions, something like that. So then we predict from 11 seconds. Our prediction is very similar to the case of magnitude 7.0 case. So next, then use up to 50 seconds. 50 seconds. Okay, so past okay, this is the present situation. So from this initial condition, we predict the future like this. Then we predict eventual distribution, something like that. So then we observe up to 50 seconds, our prediction is very similar to actual observation. So next step, next example is Sakai earthquake. In this case, earthquake occurred. And seismic propagate toward this direction, toward this casting away. So this phenomenon also observed under the earthquake occurred around here. Okay, so magnitude 6 plus aftershock, magnitude 5 plus aftershock, and this is a very, very old one, event in 2001. So anyway, so toward this way, casting away relatively strong motion propagate like this. So this is not source factor, this is path factor. Okay, so we will show our prediction. 10 second height and 20 second height prediction. Okay, once we recognize storm shaking toward this casting array, so the motion predicted like this. So next example is a Hakuba earthquake. In this case, earthquake occurred and aftershock occurred. And in this case, counter region relatively weak shaking, so the motion propagated toward the south. So this phenomenon also observed another earthquake occurred around here. Okay, so this is a very, very old one, event of 1998 event. Counter region relatively weak shaking, relatively strong shaking propagated toward the south, like this. Okay, so I will show our prediction. In second height, 20 second height prediction. Once we recognize storm shaking toward the south, we predict relatively strong shaking toward the south, like this. Okay, so this means, okay, so introduction of velocity attenuation structure is important. Okay, so no, this is the Kumamoto earthquake. There are several Kumamoto earthquakes. This is the event, largest event of the 2016 Kumamoto earthquake, but this earthquake. Anyway, this is an event of magnitude 7.0 event. So I replay with one whole speed, real-time speed. Looking at this real-time speed, seismic wave propagation seems to be slow. Okay, so during this Kumamoto earthquake, something occurred at 40 seconds. So it is easy to recognize just looking at this picture. Okay, focusing around here. Trigger event, magnitude 6 trigger event occurred. So using this numerical prediction, it is easy to predict ground motion from such trigger events. Okay, so this is a comparison of the conventional source-based method and this ground motion-based algorithm. So source-based algorithm means that from using the past to present data, all test past situation is estimated. And then, so not only prediction, but also post-prediction performance. Okay, so this ground motion algorithm using past to present data, present situation is estimated. So here, the post-prediction is not performed. And this is the first difference. And second difference is that in a source-based algorithm, very, very, very complicated way to read information, compressed, only 5 parameter. Usually, latitude, longitude, focal test, magnitude, origin, this 5 parameter. So very, very complicated phenomena is represents only 5 parameter. So this means complete lossy compression. Because of lossy compression, it is impossible to reproduce again present situation. So we cannot care about the consistency of the present situation. So now ground motion based algorithm, in this case, we keep consistency as much as possible, and then distribution, send the distribution toward the future. Okay, so in a ground motion-based algorithm, trigger-based thinking and identification of earthquake are not required. Okay, so here I briefly explain the PLUM. PLUM is already explained Norichi Kodera and Bautai. So PLUM is a simplified version of this numerical shape prediction method. The algorithm PLUM is very simple. At a nearby station, strong shaking is actually observed. In this case, EW issued. So theoretically, no restore, and we don't need to wait 3 seconds for magnitude determination, which leads to like EW. So this PLUM method is implemented in March 2018 last year. And Hokkaido earthquake is the largest event after PLUM implementation. Hokkaido earthquake focal depth is 37 kilometers, which means relatively deep earthquake. And moment magnitude 6.6, so not large, but very strong ground motion observed and 41% field. So this is the distance and observed PGA. And this is a prediction from ground motion prediction equation. Important thing for earthquake early warning is for this part. Okay, so systematic deviation from ground motion prediction equation. So deviate more than 2 sigma. Okay, so this means even when hypothetical magnitude are estimated precisely, ground motion is under-predicted. But at the time, PLUM worked well, and avoided the under-prediction. And the PLUM was earlier than the source-based method by 3.1 seconds. Okay, so I here explain the implementation of the OBS data. So SNet is composed of 150 ocean bottom seismometer deployed around here east coast of Japan. So this ocean bottom seismometer data was incorporated into JWA operation from June 2019, 3 months ago. The summary. Using this numerical prediction in which data assimilation, real-time shaping and prediction of wave propagation. So it leads to precise prediction even for large rupture and multiple events. So summary of this my presentation is, so real-time monitor of ongoing shaping enable us to predict future. Okay, so finally, several months ago, I bought smartwatch. Okay, so it is very convenient, very useful. Of course, it's phone and music player, mobile phone, alert receiver, heavy rain, tornado, and earthquake warning. So probably in near future, I guess something like that.
Earthquake. Earthquake. Intense. Again. Destructive. Soon.
And class is over, and my talk is over. 감사합니다. Thank you very much.
Thank you. Any comments or questions? Maybe one.
Interesting idea, but the whole reason why people avoid wave propagation, as far as I understand, is the amount of time that's required to do this finite difference calculations. So, how much overhead are you adding by running an extra wave propagation simulation?
It is a calculation time of the wave propagation. So in this case, there is theoretical approach. So there is theoretical approach. So much less computation times are fine difference method or battery integration method. So for example, it's a Tohoku case. The computation time is very dependent on how large that area and how much station used. So at the Tohoku earthquake case, in this case, we require 3 times the real time station. So it's not real time. But in case of the small area, just only the 60 kilometers. So in this case, faster than real time.
I have two comments or questions. The method essentially is based on the recording of strong shaking waves, so S waves. I'm concerned.
Despite the P wave from the motion to front motion.
So I'm concerned with small magnitude events, say magnitude 6 and 7. It must be some blind zone before that the technique is able to predict correctly the peak shaking beyond. Okay. Did you appreciate in your calculations how much is this blind zone and how much it compares with the potential damage zone of those effects, which is around
It's a blind zone. Yeah, in this case, blind zone defines the nearest station. The nearest station detects some motion. So in this case, we can warn around 0.
So how much is it? For magnitude 6, 7 is blind zone.
Yeah, but it's anyway. So ground motion is observation ground motion. So this is the based on this observation. This is the so we issued around here. So anyway, so prediction of ground motion. Directly is ground motion itself. So when we use the ground motion, so this ground motion propagates something like that. So blind zone, in this case, blind zone defines the nearest station from the source.
Can I have another comment? So the second is about your comment against using the magnitude, location, and GP. So the attenuation relationship that you are showing show a variability of the ground motion with the distance. Yes, exactly, which is 1 sigma or 2 sigma, etc. So this kind of variability is still in your technique because you are using some theory to extrapolate your field. And I'm not sure that you are able to account for this variability in the extrapolated your field. So I think the two techniques have similar shortcoming that they cannot resolve details in the variability of some motion.
Yeah, important thing, the point factor source information, we need to have, for example, capture directivity or vocal design or something. But it's we can observe ground motion itself. So from ground motion, distribution of ground motion, we create a future ground motion. In this case, we cannot interpret directivity or vocal design on modest event or something. But the important thing is that we cannot consider, we don't have to consider the source information such as directivity or vocal design.
Okay, thank you very much. And now we move on to the next one. So the next one is Masashi Ogiso. He will speak about introduction of a forward scattering model into the numerical shape prediction scheme.
Thank you, Chair. The topic of my talk is the improve the prediction precision of the numerical shape prediction scheme as presented by Hoshiba-san. So first, we will show the numerical shape prediction animation for the recent earthquakes. A magnitude 6.5 earthquake occurred on June 18. The left is the analysis for estimated current wave, and the center and the right the 10-second and 20-second prediction. So at time, even if you don't know where the epicenter is, you can see that the strong ground motion propagates north and south in the analysis. Then the prediction reflects such the future. So to improve the prediction precision of the numerical shape prediction, there are two key topics. The one is to improve the estimation of current wave field. For this purpose, I think that the dense seismic network is very important. And also, seismic array analysis presented by Israel group is also can be used for this purpose as well. And the other topic is to make a disk map that is to improve the calculation of the future wave field. For example, we should adopt appropriate calculation scheme or we consider the effect of heterogeneous attenuation structure. So in this talk, I focus on the calculation scheme. But we do not change the calculation scheme drastically. Same as Hoshiba-san's talk, I adopted the radiative transfer theory. The radiative transfer theory describes energy propagation, and the propagation direction of the energy may change due to the seismic wave scattering. So, there are two forms in the seismic wave scattering. One is the isotropic scattering, where the propagation direction of scattered energy does not depend on the direction of the incident waves. And this isotropic scattering model is adopted in the Hoshiba-san's talk. And the other is forward or non-isotropic scattering model. In this model, propagation direction of scattered energy depends on the direction of the incident waves. So this figure shows the difference of probability distribution of scattered wave direction. When the waves comes from left, the probability distribution of scattered wave direction is unity in the isotropic scattering model shown in black, but not unity in the forward scattering model shown in red. And the lower figure shows Green's function of seismogram envelopes based on the two scattering models in linear scale and logarithmic scales. When we focus on the direct wave part, the Green's function based on the isotropic scattering model shown in black is looks like a delta function, but the Green's function of forward scattering model shown in red is somewhat broadened or far from the delta function like shape. And this figure shows the observed seismogram envelopes. So observed seismogram envelopes looks like the Green's function based on the forward scattering model. So we expect that the forward scattering model is more appropriate for the ground motion calculation. So we used the 2016 Kumamoto earthquake for the comparison of two prediction models. And this is the distribution of observed seismic intensity. The maximum intensity was 7, which is the upper limit of the JMA intensity scale. And as Hoshiba-san already shown, this event induced magnitude 5.7 earthquake, and so this intensity distribution has two local maximum here and here. So in the prediction experiment, we used the KNet and KICKNet station shown in this map. And site amplification effect in each station was collected using time domain filters beforehand. And we used these values as the attenuation and the scattering parameters for the isotropic and forward scattering model. G0 in the isotropic scattering model is a total scattering coefficient that relates to the occurrence of seismic wave scattering. And epsilon in the forward scattering model denotes the strength of the random fluctuation of the medium velocity. And the scattering probability in the forward scattering model is calculated using this epsilon and the bottom approximation. So we show the comparison of the two prediction model, isotropic and forward scattering model in this animation. So left panel shows the estimated current wavelength. In the center, the prediction of 10 seconds ahead from the current wavelength. And the right panel shows the residuals, which means the difference between 10 seconds ahead prediction and the estimated current wavelength 10 seconds after. So red means the over prediction and blue means the under prediction. The upper panel is the result of the isotropic scattering model, and the lower the forward scattering model. So as time goes on, we could estimate the current wavelength and we could calculate the future wavelength. When we focus, this figure is very similar, but when we focus on the residuals, the red and blue pattern for direct waves is similar, but somewhat different for the polar wave part. And also the color, the residuals seems to be small in the forward scattering model. So we show the comparison of observed and seismogram observed and predicted envelopes for these four stations. Left the 10-second prediction case and right the 20-second ahead prediction case. And the observed envelope is written in black, and blue is a prediction by the isotropic scattering model, and red the prediction by the forward scattering model. When we focus on the maximum amplitude or maximum seismic intensity, the blue and the red prediction is almost the same in all of this figure. But when we focus on the whole seismogram envelope, you can see that the red envelope's prediction by the non-isotropic scattering model is closer to the observation than the blue one's prediction by isotropic scattering model. So we show the histograms of prediction residuals. The upper panel shows the residuals of maximum intensity, and lower the root mean squared residuals of whole seismogram envelopes. And left the 10-second and right the 20-second prediction cases. Although the histograms of maximum intensity residuals is very similar to each other, but when we focus on the whole residuals of whole seismogram envelopes, the non-isotropic forward scattering model resulted in a lower prediction residuals. So then we will show the next another aspect experiment. So in 2005, magnitude 6.7 earthquake occurred near Fukuoka City, shown here. And this is a distribution of observed intensities. This event, maximum intensity of this event was 6 lower, the third maximum value of the JMS scale. Probably this event caused ground shaking at the southern part of Korea. So we show the comparison of observed and seismic, observed and predicted envelope for the Fukuoka earthquake cases. So when we focus, similar to the Kumamoto earthquake cases, when we focus on the whole seismogram envelopes, except the station NGS014 written here and here, the red envelopes prediction by the forward scattering model is closer to the observed envelopes written in black. So again, we show the histograms of prediction resilience for the Fukuoka earthquake cases. And also, same as the previous slide, the resilience histograms for the resilience of maximum intensity is very similar among the two prediction models. But when we focus on the resilience of whole seismogram envelopes, the non-isotropic scattering model is resulted in a better prediction of the isotropic scattering model. This is a conclusion on future works. At least these Kumamoto earthquake and Fukuoka earthquake cases, the forward scattering model resulted in a better prediction for the whole envelopes. And this result will lead to predict not only the maximum intensity, but also the duration of the strong motions. And we expect that the heterogeneous attenuation of scattering structure in the forward scattering model will further improve the prediction. So we are trying to estimate heterogeneous attenuation scattering structure based on the forward scattering model. Thank you very much.
Thank you, everyone. Mhm.
Sorry, I was a little slow. I didn't understand the one part about the isotropicity. Where do you get in? I understood right that you need to know the direction of the wavefront moving, right? For the forward scattering? Like in the direction of the incident wave, right?
The waves comes from left to right, then this distribution scattered direction.
Right. So where do you get this information from? You extract it from the wave field? Where do you get this information about in which direction the wave is moving?
Yeah, it is very so. Sorry. So in the analysis, to make this figure, as Hoshiba-san explained, it combines the prediction and the observation. When prediction, in the prediction, we know the amplitude distribution propagation direction, and propagation direction can be estimated using data simulation technique.
As you said, arrays would be beautiful because they use the velocity, so you're allowed to reconstruct the wavefront when you have all these data points. But could you also use just particle motion directivity to feed that into the data from your three-component sensors? Not even relying on the prediction, but from the raw data to get the direction.
So in this analysis, we use seismogram envelopes, vector summation of the three-component data. So we do not use information about the particle motion. Just only use the energy.
Any more? Okay.
Thank you
Very much. And now we move on to the last speaker. The next one is Xiao Yin. We talk about estimating fault geometry from strong motion data.
Hello everyone. It's my pleasure to give this presentation for you. I'm Xiao Yin and I came from the Institute of Engineering Mechanics of China Earthquake Administration and now I'm a student. But this work is under the lead of Masumi Yamada of DPRI. So first I will show you So this big picture we have shown you many times this afternoon. So we know that this area, we have the underestimation of the intensity compared this to shaking intensity of total earthquake 2011. And we know that it's because of the point model and the rupture is really like this area. So for the Tokyo area, so it's very near to the fault, but far away from the hypocenter distance. So it makes it underestimated. So I want to do some work about to estimate the fault distance, fault geometry in real time. So this is my fault chart of my work. So I use the strong motion data and the magnitude and hypocenter location details published by GMA earthquake early warning system. And then using the GMP of these two data, I will calculate the fault distance in real time. And then I want to describe the geometry of fault using some simple models, and then we can get this observed fault geometry. And then with this, we can get the seismic intensity in real time. It's the observed seismic estimated seismic intensity. Now I'm going to the detail. First is the date, and see in this picture, the triangle is all the stations I used, and I used the strong motion date of Tohoku's main shock, and I choose the distance, hypocenter distance less than 600 kilometers. And we can also see the fault plane, which is calculated after the event and published by Shao et al. In 2011. In this fault, we can see that because it occurred in the sea, so all the stations is on one side, almost on one side of the fault. So this is the method I use to compute the seismic intensity. So first of all, the acceleration date, we use the filter which is designed to the computing the seismic intensity in real time. And then we do the vector sum of the filtered acceleration like this finger, and then do the